Okay guys, this is a repeat of the first section of last night's lecture. Actually, this is the second lecture, which has turned out to be a three-part sequence. The first part, of course, we did this on Monday night, and then Wednesday night we started to resume our lecture, and unfortunately I didn't turn on the record feature on Screencast-O-Matic, and the record feature for Collaborate don't seem to be working correctly. So I recorded half of last night's lecture, and now I'm going back and re-recording the other section. So let's go back and review like we did last night. We make sure there's a lot of terminology used in networking, and this is the problem we have in that programmable controllers are computers, and we network programmable controllers together. So a well-versed person that really wants to understand the way these things work and the way PLC networks work, there's a lot of terminology and stuff that you have to understand. And this has actually came up with some really good questions that we had in our class when we were going over the first night. So PLC networks, of course, is when we connect to our PLCs and our computers in order to share information. And that's any computer. But also, I need to come in here and say and resources. Which is one of the main things we do with a PLC, is that we share resources. So what we can do is we can literally let one PLC use an input from another PLC or vice versa. Each device, and it's actually not every device, these are usually devices that are addressable. But most just about every device that connects to the network, we have a network, and we're going to connect together the network together with some type of media. And the media itself is not a node. So this is every device on a network as a node is not exactly true because it needs to be an addressable device. So of course a computer would be a node, a PLC would be a node, a router would be a node, so anything basically that's addressable would be considered a node. But usually it's the PLC and the computer when they start talking. And of course, a protocol is a agreed upon way to do anything. So even when ambassadors and presidents and stuff have protocols that they're supposed to follow, and usually these are agreed upon. So even when a head of state is going to visit another country, then they literally agree upon the protocol that each head of states are going to follow, so they don't feed anybody off. But in networking, of course, protocols are going to be the way we connect the network together, and of course how the way we communicate or transfer information between devices on the network will be network protocols. So these are the typical types of, and there might be more, guys. These are just the ones that I know of. Ways that we connect computers, or we connect PLCs, these are primarily PLCs on a network. DH Plus and DH455, DH485, DH Plus, and DH5455. These are basically Allen Bradley interfaces, so these would be used strictly for Allen Bradley PLCs. But more and more your PLC are going over to Ethernet IP, which is also referred to as Profinet. And why this is becoming so popular is there's no really specialized equipment. All this stuff that supports the transfer of information over an Ethernet network has been around for quite a while. So this is probably one of the least expensive and most industry-wide techniques we use to transfer information between PLCs. The most widely used now is probably Ethernet, I think, just because it's a lot of devices are already out there that support this. But when we transmit this, we've got to send it over some media. And of course, we've already talked about this, but media is what information flows through. So right now I'm using air as a media. So my information, I'm going from my mouth to my speaker, and the information is flowing through the air. When we get into hardwiring or the cables, of course, we have, now of course we have something referred to as Wi-Fi, and of course your cell phone uses air as a media. Wi-Fi uses air as a media, and of course voice uses air as a media. What we're talking about here is basically when we use metal conductors to actually transfer information, which is still by far one of the most reliable ways and the fastest way to do it without depending on the air. So the first method that we use, that we're going to talk about, is a cable called coaxial cable, and we already talked about this, guys. So this sets up a characteristic impedance by the distance between the actual center conductor and also what they refer to as the shield. But the shield is actually a conductor. So this sets up something called a capacitor, which sets up a characteristic impedance rating. And we've talked a little bit about that, so we'll move on. The characteristic impedance is the overall opposition a cable experiences when a switching current is applied to it, not DC. So every cable has an R, and that's determined by the material the conductor is made out of. It's conducted by the size, which normally for round ones we call it a gauge. And then it's determined by the length. Now we can't do anything about this, but another thing we have is we have something called reactance. Now this is opposition, so R is available. It's something that's unique to DC and also AC, or switching currents. Reactance is something that happens only with switching currents. And reactance actually, the opposition actually varies with frequency. So it depends on what type of opposition we have. We have what they call inductance reactance and capacitive reactance. And I think we have just a little introduction on that. But characteristic impedance is this guy right here. So what happens is it's set by the construction of the cable. So now we understand that. What happens, and when you get into some of my classes, you'll understand that. But when all the oppositions in the entire communication system, when they match, we get maximum power transfer. So these cables have these cables are conductors that we use in communication systems, and that's what we do when we set up networks. Everything in the system is matched to a certain impedance. Impedance is a term, by the way, that we need to make sure. This will probably be on the test because it's important. Impedance is basically the opposition to the flow of AC, or a changing current that has both resistive and reactive devices in it. And definitely on networks, we definitely got a changing current all the time. So we call this a characteristic impedance. But usually when we get into AC or alternating current power, usually we refer to the opposition in that circuit as being an impedance. And impedance varies with frequency. So if we're going to get maximum power transfer, that means these cables are going to be rated at a certain switch rate that we're going to have to make sure we use the right one. So this is the cable that we're going to be using. We're going to be using a cable called twisted pair cable. And the characteristic impedance is set by the spacing, how far and this is why they have to be twisted together, and also the number of twists per inch. When it's operated at its rated frequency. Or here it would be frequency is the rate that it's actually changing. So if it's rated at 100 megahertz, that means this information is flowing at 100 million bits per second. That's what the cable can be rated at. So if you operate it below 100 megahertz, then it's not going to have the right characteristic impedance, which means we won't get impedance matching, which we don't get, and we won't get maximum transport. If you operate it above 100 megahertz, and you change the characteristic impedance, then we won't get maximum power transfer. So when we take these cables are rated at a characteristic impedance, but only when they're operated at the rated frequency. Now this is a Cat 5 cable, so these cables are given categories. And basically, the higher the category, the better it operates at its rated frequency. So Cat 5e, this is what we're doing. So this is the fifth A, B, C, D, E. This is the fifth release of the Cat 5. I think right now the highest category is 6D. I think is the one that costs the most, and it's more reliable. But when we make this cable, which is the cable that we're using, and we're going to use Cat 5e. That's actually what we're using to make our cables for our PLCs. And there's a lot that determines this. We can't get these things out of a twist very long because we'll change the characteristic impedance, which is very important. So this right here is UTP. So it's unshielded twisted pair. These would operate in PLCs that are not or networks that are not in a very high environment where we have electromagnetic interference or EMI. So this is what we're going to make because we're operating in a college. We don't have very much going on. And of course, shielded twisted pair is quite a bit more expensive. By the way, this connector right here is established by, I think it's IEEE, but I'll double check on that. And these type of cables that have this snap in, these are referred to as RJ cables. And then this is a RJ45 cable. For example, if you've got phones that use this, then that's going to be RJ11. And this gives us the spacing and the number of pins and everything. But the old phone jacks, which most of y'all don't use that now, but I still have a wired phone, but it is voice over IP. But it uses the same snap. And of course, the problem we have most often is this little latch right here will get broken off the RJ45, and then it don't want to stay. So this is just a guard that we have. And whether we use the guard or not, I have to look and see that we got some. We call this a boot, by the way, this part right here. And the main function of the boot is to provide some protection for this little latch right here. Anybody that's used a wired phone knows that usually what's happened is that little tab gets broke off, and then your handset won't stay in there anymore, or it might don't stay plugged into the wall at the back of the phone, and you'll be talking and all of a sudden it's come unplugged because This is STP cable. And so what we have is we have a metal shield that basically routes any EMI that's in the cable. It routes it out this drain wire. So this is called a drain wire that we talked about. And that's its function in life, is to drain off the EMI. And this right here would be connected to earth ground. Now to do that, when we put the connectors on there, these guys have this little metal shield around it. Oh, I guess you'd call it an enclosure. It actually makes contact with the actual connector that's on your computer or your PLC. So the computer, your PLC, down here. Well, this part right here will be metal if it's set up to use a shielded twisted pair. Now this is nothing but a strength member. It's usually some form of Kevlar or Armistead type material. So when we pull the cable through a conduit or anything like that, we're supposed to pull it by this and not by the wires. If you pull it by the wires, you might stretch it a little bit, which will change the characteristics of the impedance of the cable, which is going to cause you problems. But it doesn't mean you can't communicate. It just means that your system might drop down back to a previous standard. So right now we got 1 gigabit per second. And before that, the fastest we had was 100 megabits per second. Before that, it was 10 megabits per second. Before that, I think it was like 5 megabits per second. So what happens if your information gets garbled, then the way these network interface controllers do is they'll automatically drop back. So even though you got 1 gigabit available, and you screw up your cable and you don't build it right, or you pull it by the conductors instead of by the strength member, and you stretch those wires just a little bit, you change the characteristic impedance of the cable. So what that means is you got a 100 megabit network, but you're communicating your Ethernet, your network is dropped back to 100 megabits because it can't maintain 100 gigabits because you didn't build your cable correctly. So this is the actual connector, and the way, if you look, it looks like these pins are actually raised a little bit, and then you can't see it real well, but right here it's got a little notch. And what you do is when you insert your cable into this in the correct order, then this, when you crimp it, it pushes these little tabs down. This right here actually cuts through the insulation and makes contact with the metal conductor. Now, ours is going to be critical, but I found out from the class that some of these shells actually allow you to push the cable all the way through, and it comes through the end holes. The ones we've got is actually braced off, and then you can cut your wires off here. The ones we've got, you've got to cut them off the right length before you stick them in there. And you have to stick them in there far enough into the connector, far enough until we can actually see the tips of the wire protruding from the end. So we'll literally see So what we can do is we can actually see the wires, we can see the tips, and we strip them. So when we strip the wires, they're going to be circular. And then the metal tab, the actual conductor is going to be within inside the insulator. So when we push it in there correctly, and this is going to be copper, solid strand copper, and we should be able to see these little copper dots sticking out the end. And when we insert it in, we have to get it in there far enough so the jacket is under this crimp right here. So I'll show y'all how to do that. I found out today that I can get back on campus, so I'll go back and get some of these cables, and during our next lecture on Monday, March the 30th, we'll take a look at this. This is giving people problems. So DTE, so every network is sending information between two devices. So we have a device that originates it, and then we have a device that is the destination. This is the termination or the end of the network. So we might have all different types of devices in between us, but the two devices that we get to. But sooner or later, you're going to get the communication is going to get to the end from where it came from. So that's why these devices are referred to as data terminal equipment. So this will be your computers. This will be your PLC. This will be your printers. These will be HMI panels or human machine interface panels. These are going to be what is actually doing the communication. Data communication equipment is what the information or data flows through between the DTEs. These will be repeaters, these will be switches, these will be hubs, these will be gateways, these will be routers, and these will be Wi-Fi access. So what the information flows through to get between the DTEs is what we call data communication equipment. The actual equipment that originates the data and receives the data that is being transmitted over the network, these are what we call data terminal equipment. Very important, guys, because then this over here makes sense. So a straight through cable, when we build a straight through cable, which is what we do, these are cables that are designed to hook DTEs to DCEs or DCEs to a DCE. Now, because what we have is we have two conductors, and we'll just look at we have two conductors called transmit, and say these are pin 1 and pin 2. Well, over here on this DTE, it's going to use the same thing. It's going to be pin 1 and pin 2 to transmit the data. And let's say pin 3 and pin 4, we're making this up, guys, is used to receive data. Well, this guy is sending data out here on pin 1 and 2. If we come over here and connect that to pin 1 and 2, this guy's going to try to send information out of pin 1 and 2, and it won't work. So what we have to do is we have to take pin 1 and pin 2 in my illustration, and we have to cross these wires, right? You understand? I have to cross. I know there's nobody talking to me, but I hope you understand. We have to cross these wires. So this guy here, pin 1 and 2, would have to be crossed and go to pin 3 and 4 over here. And then pin 1 and 2 would have to be crossed and go to pin 3 and 4 over here. And these are crossover cables. We only have to use these when we connect two DTEs together. Your DCEs take care of this. They understand what this are. So a DCE will receive on pin 1 and will receive on pin 2, and y'all understand that. So we don't have to use that on DTEs. So here, what we'd have to do, we have two methods we can wire these things. These are industry standard methods of wiring using Ethernet, which is what we're going to use. We have what we call it's a TIA, TIA stands for Telecommunications Industry Association, which has come and replaced EIA, which is Electronic Industries Association. EIA disbanded back in, I don't remember the date, and it was all their protocols, hardware protocols, were taken over by TIA. But since some people learned it as EIA, normally when they give this, they give both techniques. So TIA/EIA, 568B, we have one standard, and we have a 568A standard. Even though both of these work, if you use the 568A standard to do straight-through cables, then your whole organization needs to use that. You don't need to go between 568A and 568B because you're going to get your technicians totally confused. But if you're going to use any type of equipment that allows you to monitor packets and all this other kind of stuff, they are looking for these cables to be wired as 568B. So 568B is the industry standard for straight through cables. Now why they chose that, I don't know. So what we have is we have these different colors. So twisted pair, when we come back here, you can't hardly see this, but what we have is we have a solid orange cable conductor insulator twisted with a white with an orange stripe. This is green, white, green. So green, white would be the white stripe cable. That's that pair. We have a brown, white, brown, and we have a blue, white, blue. So this is 4-pair cables, which would have 8 conductors, but it's twisted pair, and they always go in pairs. So we call this a 4-pair cable. Okay. We'll see, this is the same here, but this is UTV. But we still can't quite make out the orange twist. Right? You can see the brown real well. You can see the green real well. And you can see the blue stripe real well. So what they do, so orange, white, orange is a pair. Green, white, green is a pair. Blue, white, blue, white is a pair. So this is a pair right here. And I don't know if it's transmit or receive. I think it's transmit. And the other pair is green, white, green. And this might be received. I'm not really sure, guys. I need to look that up. Now notice they to get our EMI reduction and get the characteristic impedance, then what these two guys here are twisted together. But notice in the connector they split them by the blue-white pair, and I think they do that on purpose to. I think they do that on purpose to actually make sure you wire this cable correctly. So notice it goes orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. Now your other pair, your blue, white, blue, these are used by the local network to use for other things. So like at our college, we use voice over IP. So our phones have these RJ45 female connectors on the back. But also our phones, the RJ45 provides power for the phone. So what we're using is one of these other pairs. I don't know if we're using brown, white, brown, or blue, white, blue. I'd have to ask our network guys what they're doing. So what these do for our organization is they power the phone. Now we can still use standard RJ, we can still use the 568B standard, but they dedicated the other cables to power the phone. Now they had all the cables, and unfortunately, some of the panels that's got the connection on it where I make my connection to, some of them didn't get power. So these phones, they have to use a power supply to hook up to the phone. If you have one of the power jacks, then all you have to do is just plug the phone in and then it powers up automatically. So the only 2 pairs that's used out of all the 8 pairs, the only 2 pairs that are specified by 568B are the orange, white, orange, and the green, white, green. Use of the other pairs, your blue, white, blue, and your brown, white, brown, would be up to the organization that's installing the cables. So this is a twisted pair cable. So what we do on a twisted pair cable is one connector we're going to wire as a 568A, and the other connector we're going to wire as a 568B. We only use a crossover cable when we connect 2 DTEs. That way when this guy here transmits, it goes into the receive of other, right? You see that? And vice versa. So this is a twisted pair cable. Okay, so this is what we're going to build. And of course, the hardest thing is to arrange this and then get it into the connector after you cook off the leaves. That's why I would like to see some of them where you can actually push it through before you cut it off. So we're going to have to cut ours off to about 1/4 inch before we stick it into the connector. And then we're going to verify. Fiber optics we're not going to look at, but that's of course network topology is how they physically can arrange the nodes on the network. The first we're going to look at is a bus topology. So a bus topology, we have a common conductor, and we would call this a down drop now. And so what we do is this uses coax cable. And then what we do is we have these couplers called T's that we put on here. And then the coax snaps on here and snaps on here and down here. And then we would come over here and do a down drop. So over here we have to have this T right here. And I'm going to look and see if I can find these. But we have everything we need here to build these cables. We used to build them ourselves. And then the actual bus was run up through the plenum. And nobody knew what that was, so I'll make sure we understand that. So most of your industries use what we call suspended ceilings. So this would be the suspended ceilings. And then up here would be the actual roof. Well, this space between the suspended ceiling and the actual roof, this is referred to as the plenum. And plenum normally means it's a return for air conditioners. So a lot of buildings you'll go into, your actual return for your air conditioner, they'll just have vents up here, and then when the air conditioner pulls, it actually moves back to the plenum. Even though you don't use that, we still now refer to that as plenum. So all our cables we ran up through the plenum, and then we would have down drops that would come down and connect to the computers, and then also the PLC. Now originally, when we first got our PLCs, they did not have the ability to be networked together, as far as I know. We never networked any of them together. But this bus topology actually used coaxial cable. Now, what they've done now is they do what they call a daisy chain instead of using the common bus that runs down and use the down drops. What we use now is what's referred to as a daisy chain. This is a daisy chain. And what we do now, if we actually look at the Amatro line, and hopefully we get a chance to come back over here, we'd see that it's got these guys. And then on each one of these, it has another connector, just like the one that's on the PLC. And then what we can do is we can take another one of these and connect it to the PLC itself. So what we do is we might come in from this guy and go into here. And then this guy would go to the next one, to the next one, to the next one. So what we do on that one is basically it then away with the T's, and we just run the cables from here to here to here. Then, instead of having an actual terminator, which is basically just a resistor, what we do on the first one and the last one, so we would have this one going over here to another one. On the first one, it's got a little switch on it that we switch, which applies a terminator. And then over here on the last one, on its connector, we would switch the terminator on this one also. So this is basically the way this daisy chain technology works. Still have the terminator, but on this Profi, this over here they call it Profi bus. This is what the Amatro line uses. If we get a chance to come back over here to the mechatronics lab, I'm saying here when I'm at home, I'll go to H111 to the mechatronics lab and look at the actual Amatro PLC, the actual Amatro line. You see the Profi bus instead of the. Now this is star topology. But what has happened over time, we don't use hubs anymore. So what a hub would do was a hub would type. So if this guy, what I did in class, and even last night class, last night's class, I came over here and just assigned these numbers. Now what would happen if this node right here wanted to send information to node 4? What would actually happen? So basically a hub was just simply a repeater that we could connect all these things to. So what would happen is this guy right here wanted to send information to node 4. It would actually repeat this information to all these different nodes. Now these nodes would ignore it because this guy here would come up here and part of the packet that it sends who originated it, 1, and who it's going to, which would be 4. So all these guys right here would ignore it, but the problem is they could not communicate with anybody because the network was tied up, right? You understand? And of course this guy here would send a packet and release it, but 5 could not talk to 3 until node 1 released the packet. So what they did is they came up with what we refer to as a switch. So what the switch does when the network comes online, and anytime these guys are turned on, they would transmit a packet automatically. And that packet would indicate that I'm computer number 4 and I'm connected to this, your port. So this would say I'm computer number 5 and I'm connected to this port. This would say I'm 3 and it's connected to this port. And what the switch does is the switch comes out and learns all the MAC addresses. So this would not be a hub. What we use now is something we refer to as. So what happens now, think about a big network, computer 1 wants to send a packet to computer 4. So what would happen is the packet would go out, have all this address information still the same, so nothing's changed over here. But what the hub would do is it says, okay, this is computer 1 and it wants to connect to computer 4. So what it would do is it would connect to computer 4. But it would leave these other ports free. So now computer 2 wants to connect to computer 5. So it sends out its packet and it says, okay, I'm computer 1, I'm going to talk to, computer 2, I want to connect to computer 5. So what would happen now, and I'm going to get a different color, is this guy would come up here, the hub, it don't interfere with the communication going between, the packet going between 1 and 4, and it would come out here and it would go to 5. Now computer 3 is out of luck until the network is free. So as soon as it sends the packet, it frees up the network, and then now these guys can go in and come in there. So what happened when we came out with a switch, it greatly increased the throughput of our network. So now one node does not tie up the whole network when it's transmitting. So now we don't use hubs, we use switches. So we'll show you all a switch that's available for the Siemens PLCs. So Monday when we get back, I'll run over to the campus on the 3rd. On the 30th. We're not coming back, but our lecture will be online through Collaborate. I'll go over there and get a switch, and also I need to get make a network cable for you and actually show how that works. So a hub repeats information transmitted by one DTE to all DTEs attached to the star. Only two DTEs can communicate on the star topology using a switch. A switch learns the MAC addresses of all DTEs, only routes data from the originating DTE to the destination DTE. Multiple DTEs can communicate at the same time as long as communication is not from the same DTE that the other one is. So what happens is now multiple DTEs can be communicating with each other at the same time. On a hub, only two can communicate at the same time. Very important. Of course, this is a tree topology where we have one switch connecting multiple networks. And this might not even be a switch. I don't know how I put that. Odds are this is actually going to be a router. Well, a router basically, routers route by logical addresses. So what a router lets us to do to have multiple networks connected. And what we want to do is we don't want this guy, this network, to interfere with this network, but only when they're trying to send information, right? So what happens if this is on this network? So this, we'll call this network 1. We'll call this network 2. We'll call this network 3. And then on that, this would be computer 1. This would be computer 2. This would be computer 3. This would be computer 4. This would be computer 5. Using MAC addresses. This is going to be a little complicated. The physical address, the logical address for this, which would be assigned by software, might be 32, 33, 34. And then over here, these would have different MAC addresses, but they would also have different logical addresses. We're going to explain that in a minute. So what would happen, as long as this guy right here does not, and by the way, we call this guy right here, this is called a subnet. So a subnet is a standalone network that's part of a bigger network. So as long as these computers right here are communicating with each other, these can be communicating with each other, these can be communicating with each other without interference. What happens is if this computer wants to talk to this computer, then what it does is the router comes up and actually allows it to pass through. Then this comes over here and communicates with this computer right here. So this is the way big networks are connected together. It's going to be a bunch of subnets connected with routers. And the internet is this. So the internet has thousands of routers. And then we have all these subnets, which might be like the state of Alabama. Of course, the state of Alabama is probably subdivided. So this would be kind of like area codes on a phone system. So originally what we had is the whole state of Alabama used area code 205. And then over here in Mississippi, so we might have a phone number, 123 4, 5, 6, and the problem is with this combination right here, using decimal, we use 7 digits, so that means we could only have 10 to the 7th combination, which would be around 10 million. Would be around 10 million addresses. 10 to the 6th, 10 to the 7th would be 0. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. 1, 2, 3. It would be 10 million. Because 2 to the 6th would be a million. Right. So 10 to the 7th would give us 10 million phone numbers available using 7 digits. Well, that when we first started off, that had no problem. But the problem is now, over time, 10 million, they said, well, we'll never use all those numbers. But the problem is that eventually more and more people got phones. So right off the bat, even before we went to cell phones, they ran out of this combination real fast. So what did they do is they assigned it a subnet. We call them area codes. So now Mississippi could have a phone. Now Alabama could have a number called 1, 2, 3, 4, 5, right? You understand? And also what? Mississippi could have a number called 1, 2, 3, 4, 5. Because why? Because now they're on a different subnet. Well, what the router is looking at is the router is looking at this right here to route it to a certain state or a certain location. So originally Alabama had 205. Now I think it's got 3. Even the state of Alabama has 3 area codes. Because why? Because there's so many people now that's using phone numbers. Our phone number themselves is basically only 7 digits. But with an area code, we can repeat those phone numbers. So what that means is this guy right here could have the same logical address or node address as a computer over here, because the node address over here is on a different subnet. So this guy here would have a different area code than this guy over here. But we don't call them area codes, we call them node IDs, or node addresses. But a node ID is industry standard. But this is actually we have a network ID. We have a network ID. But it's actually a network address. Now what this does is this is basically the same as the area code on the phone system. So every logical address, these are addresses that we have the ability to, the network administrator has the ability to assign, or assigned by the local organization, or the network administrator. Now on the internet, these are assigned by the Internet Assigned Names and Numbers Authority. These are managed by that. So your network IDs are managed by that guy. And that's the administrator of the network. Now we subdivide that into countries. We'll look at that. I don't know if I've got those designators for the different countries. So this organization inside a different country, they're responsible for managing the logical addresses that's available to the internet, which we call them IP addresses, which is internet addresses. So that's the way we can divide them up. So what we do now is we have what we call a network address, and we have what we call a node address. So node addresses can be repeated. Network addresses can't. So every network on the internet has its own unique network ID. Every subnet within an organization has its own network ID. And this is what routers are looking for. So this is called a ring topology. Basically, you can see what this happens. So every node is a transmitter. And it's also a receiver. Well, these will have two network connections on the back that you can't get mixed up. One of them would be where you hook up the transmitter, and the other one where you hook up the receiver. So all these guys do is repeat. So in this guy here, if this guy, well, number them again, 1, 2, 3, 4, 5. So if this network wants to talk with computer, if this node wants to talk to computer number 5, it would put that information in the packet. So this is network 1. I want to talk to 5. Well, this guy would come over here and say, well, 5 is not me. So what would it do? It would repeat the packet. 3 say, well, 5, that's not me. I'll come up and repeat the packet. This guy would say, well, 5, that's not me. And this guy would repeat the packet. And 5 would say, hey, that's me. And it would let the packet come on into the computer. Now, the most popular method is what they call token ring. So what they do is they establish a token. So one of these guys is configured. Once you turn it on, one of these guys is configured to generate the token. And it does the token, it does it once. And then what this guy does is it comes over here and just starts passing the token around. And if nobody wants to communicate data, then what it does is it just passes and passes. So what happens now, if this guy right here wants to communicate, so what happened before, Spore might want to communicate on the network. Well, heck, it don't know 5 just sent something around the ring. 1 just sent something around the ring. So it would try to put something on the ring, and all of a sudden we have a collision. So what between two nodes? So what they would do is they came up with something called token ring. So one of these computers, and it's usually a server, is set up to start the token, and then the token starts passing around. And what happens is that if 2 wants to communicate with 5, then when it gets the token, it'll hold the token. So only the node that has the token can communicate on the ring. So 2 holds the token, it puts its packet out. So the packet goes to 3, and it says, 3 says, well, it's not for me. 4 says, it's not for me. 5 says, okay, it's me. Then it comes up here and accepts the packet. Once this guy transmits the packet, it releases the ring. So with a token ring, the only node that can put information on the ring is the node that holds the packet. So what this means, on a token ring network, there can be no collisions, by the way, even bus topologies have accepted this token passing technique to prevent collision. So one of your nodes generates a packet, and it just bounces back and forth between the nodes. And if the node needs to send packets, they'll put it on the ring. They'll hold the token. So this can be used by token passing can be used by bus topologies. It can be used by star topologies, and it also can be used by ring topologies. But this token passing technique was originally set up by token ring networks. And these were ring topologies, but it's been adopted by several of the topologies. So this is a hybrid topology. So here we're connecting basically bus topologies with ring topologies and also star topologies. And this is still popular in today's network. A ring, by the way, is very popular for network backbones. And this would be when I come up here. So this guy right here would actually be a ring topology. And then we would come back and we would go through either gateways or bridges to convert protocols. So this actually shows y'all. So DH485 is a bus topology. This is a Allen Bradley topology. The DH, which is data highway. This is a bus topology. DH485, which I left off. I need to put that. I need to put it up here because it's Allen Bradley. So this is Allen Bradley. This is Allen Bradley. Then DH455, I'm sorry, is a bus topology, but it's Allen Bradley. Profibus, this is an open topology. Anybody can use that. Ethernet, and Ethernet IP. These are the open topologies. They are currently going to be used as star for PLCs. DeviceNet is a bus topology. This is a propriety. I'll have to look at Rockwell. So Rockwell International owns the patent on DeviceNet. So a lot of Rockwell, just about almost all Rockwell networks will use DeviceNet. It's a bus topology. And then Modbus. This is an open technology that uses star or bus. Okay? I mean, I'm not why I'm asking that, because nobody's here to answer. Network access, we have token passing to prevent collisions, and we also have what we call carrier sense multi-access and collision detection, which uses this abbreviation. So anytime you see this is used by Ethernet and also Profinet. So Ethernet and Profinet uses Ethernet IP, which is, we'll talk about IPs in a minute. I think we've already talked about it even on the second lecture. Ethernet IP uses the carrier sense multiple access with collision detection, and also the Profinet uses carrier sensitive access with collision detection. All your DHs use token pathing. And we've already talked about token pathing and what I use there. Basic carrier sensitive bolt access goes through this procedure. A DTE that wishes to transmit data listens to the activity on the network media. If the network is free, the originating DTE places one packet on the network. The originating DTE checks the packet as being transmitted to see if it becomes corrupted because of a collision. So you got all these guys out there, you got 200 PLCs, and they're all listening to the network, and there's a high probability that two of them wants to send a packet at the same time. But what happens, they both go on the network at the same time, they collide. So what they're doing is, as they're putting the packet on the network, and they're checking to see if it becomes corrupted. If it becomes corrupted, what they both do is they know they had a collision, and both of them or all of them disconnect from the network. They have a random number generator that they transmit, and this way all of them won't try to come back on the same time, because it will be almost impossible for them to generate the same random number. So both release and for a random amount of time and go back to step one. If there was no collision, the packet is transmitted and they release the network. And then it keeps repeating all this until all data packets have been transmitted. This is carrier sense multiple access with collision detection. And this is what Ethernet uses, this is what Profinet uses. DH485 will come up, and we won't look at this because this is Allen Bradley, we'll use the Siemens, but this is up there, by the way, and you can search these on the internet if you're using the Allen Bradley network, and you can see how these things work. Peer-to-peer network, this is where any PLC on the network can be a master or a server, but all of them are slaves. So you have to designate a master PLC, and then any one of them can be designated a master, but all of them are considered to be slaves. A master-slave network, only one node in the whole network will be considered to be the master. And all the other PLCs or computers will be the slave. And this is very popular. This typical Ethernet network. Of course, we know that this is no longer a hub. This right here is going to be a switch. And then we got into classless and classful. So originally when they set up the internet, these buildings primarily with private IPs, what they did is they set up the internet so that we had three classes. And so using this class right here, which was called a class, something's wrong. Oh, this would be the range. It's still something wrong. This would be. I'm going to pause the lecture and go back and check and see what's wrong with this slide. I'm not sure if this was messed up on the presentation that we had last night, but when I looked at this, it said 92 to 223, and I knew that couldn't be possible. It's actually consecutive with this one. So Class A goes anywhere from 1 to 197 in the first octet. So the octet, of course, is a byte. So what we're talking about, the first octet would be over here. So we know an IP address looks like this. Then we have a dot. And then we have these numbers right here. Then we have a dot. And then we have these numbers right here. And then we have a dot, and we have these numbers right here. So what we're talking about that identifies the class is this octet right here. So if it's between 1 and 127, then it's a Class A. A Class A provides 16,777,216 IP addresses. A Class B would be, the most significant octet would be 128 to 191. So there's 65,536 IP node IDs available with the Class B. And then Class C runs from any, if it runs between 192 and 192 and 223, then that would be a Class C, which only provides, so the network ID is all these, and then the node ID would be this guy right here. So, and what we talked about this is that the Class A, these classful IPs are very, very, very wasteful. So what we'd be talking about is to identify the network ID from the, so this is a 192, so 192 means this is a Class C. So the subnet mask to identify the class, so these, the subnet mask on these were fixed. So you'll see this every once in a while when you enter a 192.168, it'll automatically pop in the subnet mask of 255.255.255.0. Now if we converted that to binary, this would be 255, so all ones would be 255, and then this would be 255, and this would be 255, and this would be 255, and then the rest of the subnet mask would be 0. So what you know about classful IP addresses, their subnet mask is going to be, for Class A, it's going to be 255.0.0.0. And then for Class B, it's going to be 255.255.0.0. And then for Class C, it's going to be 255.255.255.0. These subnet masks were built in, so a lot of times on a lot of devices, and this is also true with the Siemens 1200 PLC, once you get at this one, it'll automatically fill in this subnet mask right here, which is a Class C, which means we could have up to 256 PL nodes on a Class C subnet. It don't mean you can have, but you can have multiple subnets. So we use all the rest of this here to identify what subnet we're on. Okay. So our IP is 172. Our subnet, our network is 172.25.80. Okay, and then that subnet mask, since it falls within this range, is still a Class C, so we would use the same subnet mask. But the colleges is not 80. I think the college is 172.25.60. Then we use this right here to identify the actual computers. So what we can do is, so our subnet is different from the college's subnet for the Class C, that they're using. So, so a router routes traffic to other subnets when required. So a router would look at the network ID and decide what's route to go. As long as the route was in my subnet, then we're okay. So, one of the problems that we found is that the DNS server, we had to set up our we had to set up our server to be a DNS server. So we got our own server on our subnet. Uh, it's a domain server. So a domain on networking, I hope I got this, is a computer that runs a software that allows you to control the rights of the people that are on your network. So when you log in under MET student, then you get certain rights, but you don't get the right that I do when I log into this domain. So we get the ability to set the rights that you have. So you have rights to access this student drive that we have available for you when you log into our domain. So what we do basically is the administrator can set up what we call a script that when you load in, then we can map drives for you, so you can share that, and students is mapped for you. So it's pretty neat. So I'm the network administrator for the MET domain. So all our instructors in the MET department have access to a lot of things that they don't have to put on their computers anymore. So what the subnet mask does, it identifies what portion of the IP address is the network ID or the network address, and the actual node that's inside that subnet. So the node addresses can be the same on different subnets. What's got to be different is the network ID that identifies what network that computer's in. And just like we said, the area code is 205, and I don't know what the other ones I should, but it might be, I can't remember what it is, 233 or something like that. Well, I can have a 4246728 up here, and I can also have a 4246728 down here. But what it is they're on a different subnet. So these area codes are exactly the same, and that's the way the switchgear so basically the switchgear that's part of the telephone system is nothing but basically routers, and they don't look to decide which area to go into. They're not looking at the phone number, they're looking at the area code. And so when the routers see a 205, they route it to us, or where I'm at. If it sees a 223, it routes to the other one. If it sees the area code for Michigan, then it goes through different paths to get up into Michigan. And there's probably a 4246728 up in Michigan somewhere. But it's on a different subnet. It's in a different area code. So, which is pretty interesting. So these are the built-in subnet masks for the three classes. So Class A would use this subnet mask, and then Class B would use this. This says this is the network ID here, and then this right here has the network ID right there. So Class C. So the college is running a Class C network. Well, used to run our the PLCs are running a Class C. So this is actually the subnet mask breaking down into binary, and to actually see the network IDs. Of course, with classful IDs, it's real easy to see because it's set up in it's set up so that each octet is represented in a subnet. So with a Class C, when you see 255.255.255, let's say 78.53, it's real easy to see. These are the 255s up come here and tells us that this is the network ID, and 53 would be the address of the node within that subnet. So these classful, it's real easy to see. It's real easy to see the break. In a classless, you have to come in and you have to look at it a little greater, because the classless, it can actually break anywhere. So Class C, and we looked at this. Classes. So classless, what we do is we define basically the subnet mask, where the ones belong. So we really don't have to come up with the subnet mask, but we identify it within the address for the IP. So what we're doing, so a /25 would mean after the IP would tell the router that this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Did I miss one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So a /25 would designate that the first 25 bits is the subnet mask, or I'm sorry, is the subnet. And then the rest of this would be the actual network ID. So that means 1, 2, 3, 4, 5, 6, 7. We could represent 2 to the 7th, which would be 128 node addresses. And then this right here would be the subnet mask. So the subnet mask would actually be 255.255.255.128 would be that. So the college is using a classless /25. So I just put these in lately because Capri is dealing with this classless internet domain routing, or CIDR, at work, and we wanted to explain this, or she wanted to know a little bit more about it. So I stuck these slides in here because this is not necessarily used by PLCs. Most of the PLCs that I've seen uses a classful IP. I mean a classful a subnet mask. So, and I think when we set up the, we'll pop up and see if I can get the tail portal up, and we'll go in and look at the IP address on the IP address for the 1200 PLC, and we'll see what it says. So a /25 subnet mask, what would be the college subnet mask? So what we would do is we'd come up here a /25. Let me go from my current client side. So a /25, the subnet mask would be on /27 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 25, 26, 27. And then the rest of this would be node IDs if I got enough room, guys. So that means we got, so that'd be, subnet mask would be 255.255.224, which would be this guy right here. So that's going to be 1, 2, 3, 0, 0, 0, 0, 0, 0. So this is going to be 1, 2, 4, 8, 16. Uh, 32, 64, 128. So I'd add 128 plus 64 plus 32. So this would be 4. This would be 2. This would be 2. So 224. This is a subnet mask that they're using. So it's a /27. So in binary it would be 1, 2, 3, 4. I tried to write it up there, but I got a little room down here. 4. 1, 2, 3, 4. And it's easy to put the dots. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So that would be 255. 1, 2, 3, 0, 0, 0, 0, 0. So 1, 2, 1, 2, let's see, 1, 2, 3, 4, 5. So it's 2 to the 5th, which would give us 32 computers on the subnet. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 2 to the 5th. So if a network only has 15 nodes, it would have to use a Class C subnet mask that allows 256 nodes. This would mean 241 IP addresses would be wasted. So classful IPs are very, very wasteful because you gotta use a class no matter how many computers you got. So if I've got 259 nodes, then I would have to use a Class B, which provides 65,536 node addresses. So I've wasted quite a bit. So we looked at this. Does not use a classful subnet mask to define the network ID or node ID. Uses a classful IP address followed by a slash by the number of, like I said, I just put these up here, you guys, so it's got a few errors in it. By the number of bits used for the ID. Okay. And IPv6, so we needed, this is going on with internet. Since they came out with classless IP for the internet, this has basically extended the life for the IPv4. And what it did, it allowed domains that were out there, or web servers that was out there, to keep their original IP address. And then they modify the IPv6 to identify that, but it's really neat the way they do that. So I think last time I looked, the United States is like 66% of the web servers, or the different servers. We call it World Wide Web, but there's FTP servers out there, there's mail servers out there, there's internet relay chat servers out there. We just don't, it's kind of transparent to us now because our web browser, our browser, our internet browser, it used to be, when it first came out, it was called a web browser because those things could only access World Wide Web servers running the HTTP, the Hypertext Transfer Protocol servers out there running for that. But what's happened is, and then we had to have another application to access FTP. We had to have another application to access chat rooms. We had another application to address email. But now, just about every one of those protocols or applications are included in what we call a browser. So it's an internet browser now. It's not necessarily a web browser, but some people still call it that, but it's an internet browser. So just about all our browsers, like Microsoft Edge, like Chrome, like Mozilla Firefox, these are actually have all of these FTP and all these other servers, all these other applications embedded inside there. So that means we can have we can chat on Microsoft, on Facebook Messenger, which is nothing but a chat. It's nothing but an IRC, but it's embedded inside the application, and we can do that now. So a IPv6 is a 28-bit number, guys. We could have two at least. It's actually 2 to the 28th if you want to see the actual number. 2 to the 128th if you want to punch that into your calculator and see the actual number. In fact, what I'll do is I'll bring up my my calculator, and I'm going to put 2 raised to the 128th power and I'm going to equal. So that's my calculator can't even do it. So my calculator actually pounced into scientific notation because it could not represent that number with it, and it's a large. Your calculator wouldn't even have a chance because your calculator probably calculates 13 bits, but it displays 10, so it can round correctly. So it'll jump into scientific notation early, and it won't give you as many digits as this guy did. So this is how many digits this calculator right here can display for us. So this is what we went through these last night. So these were all recorded on the other lecture. So I'm fixing to stop right now, and I'll go ahead and upload these lectures. Like I said, I don't know what's going on with the recorder inside of Blackboard Ultra, inside Collaborate. I think I showed y'all last night that it's not doing what it's supposed to do. So I'll go ahead and pause this and go ahead and exit the room, and then I'll upload this probably tomorrow. Hope you have a great holiday or great break, and stay out of trouble, and I hope you stay safe.